Okay, so welcome guys sa continuation of discussion natin for Flexural members. So for this afternoon, we will be focusing our topic or our discussion with the design method or how to design yung given um, beam natin when it's subjected to the following loadings, no, or different loading conditions. Okay, so our outline for today will be, hindi ko pala nakashare yung aking wait lang. Okay. Ayan. So, yung outline natin for today, ayan. So, design of flexural members. And then, pakita lang natin kung paano siya sinosolve by trial and error. And then, using design chart ni AISC. Okay? Pero may limitation kasi yung design chart kasi um, para lang siya sa conventional values ng FY or ng grade ng steel natin. And also, applicable lang siya for English units, no? Walang design chart prepared for metric. So, usually ginagamit yung design chart kapag English system yung values natin. Nasa case natin sa Philippines, syempre, metric tayo. So, to use yung design chart, we need to convert yung values natin into English to use also the table. Okay? So, outcome natin for today to demonstrate how the two design processes or approaches are applied on examples and design the beam section to carry yung given loading natin. Okay? So, beam design entails the selection of a cross-sectional section that will have enough strength and that will meet serviceability requirement. So, nakalagay dito serviceability requirement. So, hindi lang flexure yung kailangan natin satisfy. Kailangan natin satisfy yung serviceability, which is yung deflection natin, yung discussion natin yesterday, no? And then, ito, in-outline ko yung design process na pwede nating sundan on how to select our most economical section to carry yung mga loadings natin. Okay? So first step is to compute the required moment strength. So with the given loadings, identify natin yung ultimate moment or allowable moment using yung load combinations natin for LRFD and ASD. Then after identifying yung ating ultimate moment, okay? So after, 'di ba, yung ultimate moment natin and then yung MA natin, kailangan kunin natin yung required na nominal moment natin. And yung required natin, yung MU natin should be equals dun sa VMN natin. Okay? So, later na tong sa ASD. So, para ito yung required natin, no? Ibig sabihin, ito yung capacity ng section natin. And alam natin na si VMN, ang formula niya, if i-assume natin na compact yung section sa start, no? Ang formula niya, ang MN ay equal sa MP, no? Katulad nung yung sa yielding natin na formula. So, ibig sabihin, ito is VMP equals sa V FYZX. Okay? So, kapag na-calculate natin yung ultimate moment natin using yung load combination natin, ang kailangan natin kunin para makapag-select tayo ng shape is kung ano yung required na ZX o yung plastic modulus natin. So, ZX is equals to MU all over VFY. So, ito yung kailangan natin kapag LRFD yung kinakalculate natin. Pag allowable naman, equal sa dun sa MN over omega natin. So, this will become yung plastic modulus natin over omega. Then, we will have Fy Zx over omega. So, if we need to calculate for Zx using ASD, so that will be omega MA over Fy. Okay? So, yung factor natin nasa taas. So, depende na lang sa hinihingi sa problem kung ano yung gagamitin natin value, no? So, sa LRFT, and then ito ay ASD. Okay? Ayan. So, once may value tayo ng ZX, ngayon magsaselect na tayo ng shape. And we can select yung shape by two methods. We have yung trial and error method and then by bin design charts. Okay? So yung trial and error method, after mo makuha yung ZX, pupunta ka dun sa table natin for cross sections. And then hanapin mo yung ZX na column. Then kunin mo yung lahat ng sections na mag-start from the smallest, no? So let's say, let me share yung ating section. So halimbawa ito yung shape natin. Okay? So halimbawa may nakuha kayong value ng ZX. Okay? So nakuha mo ZX starting from the bottom. So kada group ng section, meron tayong 4, 5, 6, 8, 10, 12, 14, 16, 18, 21, 24, 30, 33, no? So yung mga sections natin. Kukuha ka ng tigi-isa sa kanila hanggang makuha mo yung lightest na pwede. Pag halimbawa yung section dun sa next na group ng sections natin, halimbawa from 21, may nakuha kang section, and then pagpunta mo ng 24, imbis na mas gumaan yung section, mas bumigat pa siya, mag-stop ka na doon and lahat ng na-select mo, yun na lang i-check mo for um, trial and error. Okay? Then sa trial and error, kailangan i-satisfy natin, syempre, yung required na ZX natin. So yung ZX na actual should be less than dun sa required natin, no? Kasi para masabi natin na sufficient or adequate yung section natin. Okay? Kung nakuha natin na less than nga siya doon sa ZX natin, pwede natin i-check ngayon yung section natin for shear and for deflection. So bakit tsaka mo lang siya i-check? Kasi based from from other studies or other textbook, as far as that is concerned, kapag beam yung pinag-uusapan natin, flexure is always more critical than shear or yung ating deflection. So yung usual practice is to design muna for flexure and then tsaka mo na lang check for shear and for deflection. Now, kapag hindi siya pumasa ng deflection or ng shear, ibig sabihin, mas governing yung shear or yung deflection. And then from the formula for shear and deflection, kukunin niyo yung required na values doon. And then tsaka ka ulit trial and error para mag-select nung mismong section natin. Okay? Next, by design chart, no? Pag by design chart ang gagamitin, babalik tayo dun sa AASC natin. Okay? So sa AASC, kapag tingnan natin table 3-2, yan, selection by ZX. So dito naka-indicate yung value ng ZX na required mo. So yung mga calculate natin, kailangan i-convert natin sa inch cube. And then lahat ng values na yon, sa-select mo dito. Halimbawa, ang nakuha mo is 500, no? Hanapin mo ngayon yung 500, pinakamalapit sa 500. Yung pinakaunang section, siya yung lightest na pwede, no? So 500 yung nakuha kong ZX sa calculation ko ng MU, no? ZX ko 500, so 500 rin yung pwede. So pag chinek mo tong 135, yung naka-bold na unang section dito, siya yung pinaka-economical dun sa group na yon. Pag hindi siya okay doon, you can select the next one, which is 30 by 148. Okay? Pero if you want a more lighter section, pwede kang mag-move dun sa kasunod na 514 plus 141. As you can see, mas magaan si 141 kaysa si 148. So, depende din sa clearances natin. No? So, kung halimbawa, mas magaan nga si 141 pero sa actual site natin, si 33 is magiging parang halimbawa naka-nosing na siya. Eh, minsan si architect ayaw niya na naka-nosing. So, baka mas appropriate si 30. Kaya ito yung gagamitin natin 30. Okay? So, laging depende sa designer yung decision nito. Kasi nga, nagde-design na tayo ng section. Pero, andito yung shape, yung table na to guide us to select yung lightest section modules natin, no, na pwede. And then, you have to check na lang to verify what will be the value niya. Makikita niyo dito, may value na agad siya ng ng value ng moment capacity niya. Okay? And also, both ASD and LRFT. Tsaka dito ma-check mo din yung LP, LR and yung LP and LR natin na ginagawa natin to check kung pag hindi fully restrained yung atin, kung Halimbawa, inelastic LTB siya, elastic LTB, or no lateral action, no? Lateral torsional backing. And then meron din dito yung para sa shear strength check natin. So hindi ka na kailangan mag-calculate, no? Pero later papakita natin na yung diniscuss natin last session, yung pag-calculate ng shear natin. Okay? So let us proceed with an example so that we can understand more kung paano natin ginagamit yung mga sections na yan. Okay? Going back to sa slide natin. Ayan. So let's have our first example. Okay. Select a standard hot rolled shape of A992 steel for simply supported beam with a span of 10 meters. So let us siguro draw. So we have a simple span lang. Okay. So ang length natin is 10 meters, no? And then the beam has continuous lateral support. So pag may continuous lateral support tayo, ang ibig sabihin, ang MN natin ay equals kay MP, no? Or zone 1 tayo. Okay? And must support a uniform service live load of 65 kilonewton per meter. So meron tayong continuous load na 65 kilonewton per meter, pero ito ay live load lang. The maximum permissible live load is live load deflection is L over 240. Okay? And yung atin ay A992 steel tayo. So kailangan natin yung FY niya. Okay? So yan yung given natin. So kung walang given na FY, you just need to go back to your AISC and then go to table 2-4. Then tingnan nyo yung A992. A992 is 50, ang FY niya ay 50 KSI. Okay? And 50 KSI, kapag kinonvert sa MPa, times mo lang ng 1,000, divide 145, makukuha natin ay equal sa 345. Okay? So, ibig sabihin ng equivalent na 50 KSI in MPa ay 345 megapascal. Okay? Ayan. So now, pwede na tayo mag-start ng analysis natin. With the first one, identify natin yung MU natin. Okay? Okay, so MU natin, so ating distributed load will be equals to 1.2 WD plus 1.6 WL. Okay? So dito walang given na applied o superimposed dead load, pero di ba yung steel beam natin is meron siyang weight, self-weight, no? Pero for a more conservative assessment, pwedeng i-neglect muna natin yung weight ng beam. So ang gagamitin lang muna natin is yung live load na 65 kN per meter. Okay? Kasi kung yung self-weight yung pinag-usapan natin, it's very small comparing it with the superimposed load natin, like the live load or dead load kung meron man siyang applied sa kanya. Okay? So dito, initially, 0 lang to, plus 1.6 times yung live load natin na 65 kilonewton per meter. Okay? So ang WU natin is equals to 1.6 times 65, that is 104 kilonewton per meter. Then we need to calculate for the ultimate moment. So WL squared over 8, that is 104 kilonewton per meter times 10.0 meter squared all over 8, or yung maximum moment natin, or ultimate moment, 104 times 10 squared all over 8, so 1,300 kilonewton meter. Okay? And then, we proceed with the selection ng members. Para ma-select, we need ZX. ZX is equals to MU all over PFY. Okay, para makuha natin yung ZX required. So, this will be 1,3, times ko ng 1 million para maging Newton mm all over. P natin is 0.9 kasi nga lateral strain tayo all throughout. So, Fy natin is 345 Newton per mm squared. Okay? So matitira sa atin is mm cube. So 1,300 times 10 to the 6 all over 0.9 times 3.5. 345, we have 4,186,795.491 mm cube. Or pwede kong sabihin na lang to na 4,187 times 10 cube mm cube. Okay? So, ito yung titingnan natin sa table natin sa pagsa-select ng section natin. Okay? So, going back dun sa ating table. Okay? Again, yung value natin is 4187. Itong ZX natin dito, as you can see, ito yung mga values niya. So, starting from the bottom, okay, ito yung pinaka, ano natin, mali. Tingnan natin yung ZX. Yung ZX natin, pag tinignan natin ito sa README, is, nasan yan? ZX. Ang unit niya is times natin ng 10 cube over mm cube. Kaya ang ginawa ko dun sa ano natin is nilagyan ko ng scientific notation yung dun sa slide natin. Ginawa kong 4187 times 10 to the 3, no? Kasi yun yung basis natin. So 4187 ang kailangan natin. So 4187, 4187. So far wala pa. 4187. So first section natin is ito. Start tayo ay sa gawin natin kulay. Gawin natin violet na lang. Huwag masakit sa mata. Ito na lang, orange. Okay? Yan. So ito yung unang section natin. So ano yung kailangan natin ilista kung mag-create tayo ng section. So although ako na lang magsusulat, no, ang kailangan natin is yung trial section. Okay? Then ano pang kailangan natin na pwedeng gagamitin natin? Kailangan natin ng weight niya. Okay? And also kailangan din natin yung kanyang plastic modulus of elasticity. Okay? Ito yung first trial section natin. So W 12 by 170. Ang weight natin sa kanya, tingnan lang natin dito. Wait. Ayan to. 253 daw yung weight niya. And dito, pag tingnan natin yung readme, yung W dito, ang unit niya ay kilogram per meter. Okay? So, kunin natin to, 253 kilogram per meter. Then yung ZX natin, balik tayo doon, yung tingnan natin kanina. Yan, ZX natin is 4,510. Yan ay times 10 to the 3. Okay? Next. Next section tayo sa W14. 4187 ulit yung kailangan natin. 4187, so ito, pwede ito. W14 by 145. So, W14 by 145. Ang kanyang CX is 4260. Then yung weight niya is 216. Okay? So, 216. Next. After ng 14, punta tayo sa 16. Tapos 4187, so walang 16. Sa 18 tayo. Yan, 4290 yung kasunod. So, W18119. Ang kanyang ZX is 4290. And ang kanyang W is 177. Okay. Next. After W18, W21. 4187, 4187. So, ito, 21 by 1111. Okay? So, W21 by 111. Kunin natin yung ZX ulit, 4570 times 10 cube. And then, yung weight natin sa kanya is 165. Okay? Again, hanggang hindi, kung patuloy na lumiliit yung weight natin, tuloy lang natin. Next is 24, 4187 sa 24, dito na siya papasok. So W24 by 103. So ang ating section modulus is 4590 times 10 cube. And then ang ating weight ay kulayan natin 153. Okay? Next, after ng 24 by 103, next natin is 27. Pero 27, 94. Okay? So, lumiit pa din siya, no? So, W27 by 94, and then 4560 times 10 cube. Then yung weight natin sa kanya, saan yan? 140. Okay? Okay, next, W30. W30 is 4640. Pero by 90 siya, so pwede pa din. So W30 by 90. So 4640. Tapos yung weight niya is 134. Okay? So, haba, no? Next, W33. Sa W33, ito yung next section na pwede sa kanya. Kaso makikita ninyo, naging 118 na ulit siya, no? From 90, 118 ulit. So, ibig sabihin, si W30 by 90, yung lightest na pwede natin gamitin. Okay? So, stop ka na muna doon. Okay? So, kapag nakuha na natin yung pinaka-lightest, yung list ng sections na pwede natin itry for calculation, doon na natin siya ngayon i-check, no? Okay, so ito yung mga nalista ko. Okay? So, okay, from the bottom, ito muna yung una natin i-check, pataas tayo, no? Kasi alam natin na ito yung lightest possible given yung ZX natin na yan. Okay? So, paano yung pag-check sa kanya? So, kailangan i-calculate natin yung um, yung yung ZX ng section, yung actual Z kapag gamit natin yung section na yon. Kasi 'di ba, kinuha natin yung weight. So, meron na tayong value for self-weight. So, meron tayong makukuhang value ng bagong value ng WU, and then meron tayong makukuha na bagong value ng ZX. Dapat yung ZX na makalculate natin is less than do sa section natin. Okay? So, wait. Ano natin, no? Lagay natin sa Excel, no, para hindi tayo paulit-ulit ng sulat. Okay? So, again, kailangan natin i-calculate yung mismong ano natin. So, share ko lang yung Excel file. Ayan. So, may Excel ako dito. Ayan. So, ito yung nasulat nating ano. So, start muna tayo dito sa first condition natin. Okay? Dito sa first section natin. Ito. Okay. Ayan. So, ito muna. So, kailangan natin calculate is yung given yung weight natin. Ito yung section natin. Ito yung ZX natin. Okay? Calculate natin ngayon yung given natin na WU, WD. Okay? According dun sa weight. So, una natin is W30 by 90. So, ang weight natin sa kanya is 134. Pero ito ay kilogram per meter. Kailangan natin ay kilonewton times kilonewton per meter. So, ta-times natin ng 9.81 para maging newton. Okay? Tapos divide natin by 1,000 para maging kilonewton per meter. So, ito yung value niya for kilonewton meter. No? Yung sa live load natin, magkaano yung sa live load natin? We have 65 kilonewton meter. So, ibig sabihin ng W natin ngayon is 1.2 times yung WD plus 1.6 times yung ano natin. So ito na ngayon yung U natin. So para makuha natin si MU, okay? So lagay lang natin dito yung length natin para later magamit natin sa next problem. 10 meters yan. So WL squared over 8. So W times L squared natin over 8. So ito yung moment natin. Kilonewton meter to. Okay? And then, ano yung calculate natin ngayon? Yung ZX actual natin. Okay? So, equals MU all over yung value natin na 0.9. Lagyan natin ng quantity, 0.9 times yung FY natin na 345. Okay? So, yung moment natin kailangan naka-times ng 1 million para Newton mm yung kanyang unit, no? Um, times 1 is 6. Ayan. So, tapos divide natin ng 1e cube para maging ito yung 250 times 10 to the 3 mm cube. Ito yung actual natin. Yung ZX ng section natin is yung nakalagay dito 4640. Okay? Kapag yung section natin, kapag yung ZX section natin ay less than do sa ZX actual, not good yan, no? Okay? Tapos good siya kapag greater than siya. So, ibig sabihin, hindi pwede yung first trial section natin. Lagay natin dito sa remarks, yung code, remarks. Lagay natin, if yung actual natin is less than dun sa section natin, Z ng section, ZX actual. Okay. If less than si section, kay actual, ano ba? Kapag less than si section, dun sa actual natin, not good siya. Kasi nga, hindi, ibig sabihin, hindi kayang um, tama ba? Wait lang ha. Balik tayo dun sa slide natin. Kapag kapag yung ZX actual natin is less than dun sa section, okay tayo. Okay. Okay. Yun pala. Okay, wait lang. Okay, going back dito. So, kapag yung section natin is less than dun sa Z section is less than dun sa actual, not good. So, pero dito, yung Z section natin is greater than dun sa actual natin. So, ibig sabihin, kaya natin i-carry or kaya niyang i-carry yung required natin. Okay, so, if yung Z section natin ay less than dito, tsaka siya magiging not good, no? And then, tsaka siya good kapag na-satisfy niya. Okay? So, since good yung design natin, lagyan natin is okay. No? Parang, okay? So, since pasado siya dito, ibig sabihin we can use yung 30 by 90 as our section. Okay? Kasi pasado siya dito sa condition natin dito. Okay? Therefore, sa flexure, pasado na si W30 by 90. Okay? Next is to consider yung shear natin. Okay? So going back to sa slide natin. So, based dun sa Excel, um, therefore, W30 by 90 is adequate for flexure. Okay? So, ang capacity na nakukuha natin is 1319. Okay? Okay. Next is to check kung yung mga step natin. Check for shear strength. Okay? Check for shear strength tayo. Shear strength. So, VBN natin. Yung formula natin from yesterday's discussion. So, we have yung 0.6 FY. No? Yung 0.6 FY AWCV. Okay? So sabi natin, kailangan natin satisfy muna si H over TW. Okay? Na ang kailangan natin property sa kanya ay D minus 2K1 all over yung value ng TW natin. So, yung W, 30 by 90 natin, kukunin natin yung section yan dun sa table natin. Okay, ito. Kailangan natin ng value ng D. So, value ng D natin is ito, 749. Value ng K1, 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 K1 to 36.5. And then yung TW natin, thickness ng web is equal sa 11.9. Okay? So, going back to sa slide. Okay? So, ayan. So, substitute natin. 749 minus 2 times 36.5 divided by 11.9. So, yung H over TW natin is equals to 749 minus 2 times 36.5 all over 11.9. We have a value of 56.807. Okay? So, let us check yung ating um, yung discussion natin yesterday. Let me pull up lang yung slide natin. Okay, so ito yung discussion natin yesterday. So, yung VN natin is 0.6 FY AWCV. So, kailangan check natin sa 2.24 square root of E over FY. Okay? Okay, so wait lang, double check ko lang yung solution. No? Okay, so kunin natin yung 2.224. E over Fy. Okay, so ito yung kailangan natin satisfy. 2.24 square root of 200 times 10 cube. all over 345. So yung value natin, 2.24 square root of 200 times 10 to the 3, 345, that is 53.933. So ang H over TW natin is greater than so 2.24 natin. Okay? So double check ko lang kung tama yung solution. 36.5 all over 11.9. Yes, no? So kung greater than, tingnan natin tong diagram dito. For webs of double symmetric shapes and single symmetric shape and channel. So, ito, pwede pa naman tayo ditong mag-fall under sa second na condition kasi doubly symmetric eye shape tayo, no? Um, we have to get yung value nito, no? Yung H over TW natin is less than 260. So, we can assume na yung value ng KV natin is 5. Okay? So, KV natin is 5. So, i-follow natin yung value dito. Okay? So, sulat ko lang yung mga formula. So, kailangan natin nung 1.10 kVE over Fy. And then we need yung 1.37 square root of kVE over Fy. Okay? Okay. So, going back do sa slide natin. Okay. So, dito, 1.10 square root of 5 times 200 times 10 cube all over yung 345 natin. This is equals to 1.1 square root of 5 times 200,000 divided by 345, that is 59.22. Okay? So, yung value na yun is yung HTW natin ay less than ng 1.1 square root of kV E over Fy. Therefore, yung CV natin is equals to 1.0 according na din dito sa table natin dito. Okay? Ayan, yung first condition natin. Okay? So, pwede na natin continue. CV natin is 1.0. So, calculate natin yung value ng nakalagay doon. Since nandun na tayo sa second one, ang magiging value ng fee natin is 0.9. No? So, yung VN natin, PVN is equals to 0.9 times 0.6 FYAW CV. So, this is 0.9 times 0.6 times 345 times yung AW natin is multiplication lang nung D times TW natin. So 749 times 11.9 times 1.0. So ito yung magiging value ng shear natin. 0.9 times 0.6, 345, then 749 times 11.9 times 1. Okay? So makukuha natin, is 1660.510 kilonewton. So ito yung capacity ng section natin. So ano yung magiging VU natin? VU natin is, since simply supported yon na uniformly distributed, WL over 2. Okay? So yung WU natin from our Excel kanina, kung na lang kukuha, yung WU natin is 105.58 times 10.0 all over 2. So VU is equals to 105.58 times 10. Divide natin ng 2. That is 527.9 kilonewton. Since yung VU natin is less than ng VBN natin, therefore, okay tayo or section is adequate for shear. Okay? So, adequate din siya for shear. Next, check natin siya for deflection. Okay? So kung for deflection, ang allowable natin is for live load lang yan, no? So live load lang yung loading natin. So L over 240, that is 10,000 over 240. So kailangan, yung value natin is dapat 41.67 mm or less. Okay? So according sa formula, we have 5 over 384 W L to the fourth over EIX. Okay? And ang IX natin, kukunin natin dun sa ating table. Okay, ito. Then kunin natin yung IX natin. Ito. IX natin is 1,500. 1,500. Then tingnan natin yung unit ng IX. IX dito is, ayan, IX natin is times 10 to the 6 mm to the 4th. Okay? So, calculate natin yung actual deflection natin. Okay? So, this will be 5 over 384 times yung W natin is for ano lang, live load lang. So, ito lang yun, no? So, 65 kilonewton per meter ay equals din sa newton per mm, no? So, ito ay newton per mm times 10,000 the fourth all over. E natin is 200,000 and I natin is 1.5 times 10 to the 6. Okay? So, yung actual deflection natin is 5 over 384 times 65 times 10 to the 3 to the 4th all over 200,000 times 1.5 to the 6. Okay? Value natin is 30.603 mm, which is less than dun sa allowable natin. Therefore, okay or adequate for deflection. Okay? So therefore, use W 30 by 90 structural steel beam. Okay? So, yung magiging section natin, lightest section na pwede natin gamitin for this loading. Okay? Question dito sa first example for verification. No question. Hello? Okay, let's continue. Okay, so second example, select the lightest W section to carry a uniform dead load. Okay, so before we proceed dito, try natin by design chart, no? So ito yung nakuha nating value ng mm cube, no, di ba? So gamitin natin itong value na to using yung design chart natin. Okay? So gawin natin, ito yung nakuha nating capacity ng ZX na required. So convert natin sa diba, 25.4 mm is 1 inch cube. So 4187 times 10 to the 3 over 25.4 cube. So we have 255.51 inch cube. ito yung i-check natin ngayon dun sa ZX table natin. So, let us go to AISC. Dito. Okay, then going dito sa table 3-2. Kailangan natin is 255 and greater. So, punta tayo dun sa ZX na column and then punta tayo dun sa 255. Then sa 255, ang pinakamalapit, ito, yan, sa 283 natin dito. Ayan. So, makikita nyo, nakalagay agad sa kanya, W30 by 90. Okay? Tapos, ang capacity niyang ZX ay 283 inch cube. And then, ano pa? Kunin natin yung value ng moment capacity niya, 1060. 1060 keep fit. Kailangan mo natin is yung kanyang sa shear niya. So shear VN niya is 374 keep. Okay. So as you can see, mas mabilis, no? Na-identify na agad natin yung section. Pero meron siyang nandito, no? Mayroon siyang nakalagay na V, no? Dito. Na ang sabi niya, shape does not meet the H/TW limit for shear and AISC, no? Kaya nangyari dun sa ano natin, dun sa kanina, hindi nag-later na siya dun sa 2.24 kaya hindi niya na-meet, no? Pero upon checking yung another formula, nakita natin na CV is also equals to 1.0 pero ang kailangang value natin ng PV ay 0.9 na. Kaya makikita nyo kanina doon sa solution natin, 0.9 na yung ginamit natin. Okay? So going back to sa slide natin, okay? So ito yung property ng W30 by 90. So kung sa moment lang, kung ang pag-uusapan lang din naman is yung ZX natin, okay na siya dito sa moment capacity natin. Okay? And then yung sa shear natin, 2374 yung capacity niya. Ano bang conversion ng kips to kilonewton? So let me get nga lang a conversion. Kips to kilonewton. So ang 1 kip ay equals sa 4.45. 4.45 ng kilonewton. Okay? So syempre itong value na to, dapat same to nung nakuha nating value kanina. 4.45 kilonewton equals to 374 times 4.45. So 1664.3 kilonewton. Okay? Na-calculate natin from the previous slide is 1660. No? So, malapit yan dun sa kinalculate natin. 1660 na calculate natin and yung given dun sa table is 1664. So matter of conversion yun ka, may discrepancy konti na 4 kilonewtons. Pero once na na-select na natin tong section na to, yung procedure for checking is the same na nito. No? So for shear, ko-compare mo na lang siya doon sa VEU kasi meron na sa table ng VN niya. Ko-compare mo na lang dito. Then yung sa deflection will be the same na. So yung sa using the design chart, makikita natin na use din natin yung W30 by 90 na section natin. Okay? So yun lang yung sa using design chart natin. Pero again, limited lang siya for this for strength na Fy is equals to 50 KSI o 345 and kailangan yung ZX na gagamitin natin panghanap dun sa table is dapat in terms siya ng English system. So, kung kaya naman natin sundan itong solution natin na to, no? Mas maganda to, no? Kasi kung magagawa mo siya ng spreadsheet, mas mabilis ka makakapag-calculate nung pag-check nung isa-isa nung section natin as our trial section. Okay? Okay. So, next question, select the lightest W section to carry a uniform dead load of 7.5 kilonewton per meter and a live load of 15 kilonewton per meter on a simple supported span of 13 meters. Adequate lateral support is provided. So the live load deflection is limited to L over 360. Use A672, rate 50, and LRFT. Okay. So we again have a simple supported beam. Okay. So ito yung ating WU. Then ito is 13.0. Okay. So ano pang ano natin? Ang FY natin is 50 KSI, grade 50. So that is 345 MPa. Given pa natin, ang WD natin is 7.5 kilonewton per meter. Ang WL natin is 15.0 kilonewton per meter. So live load na allowable natin is equals to L over 360. Okay? So, calculate natin yung ating MU. So, W, U is equals to 1.2 WD plus 1.6 WL. So, 1.2. So, neglecting self-rate muna ulit. So, meron tayong superimposed dead load. 1.6 ng 15. So, WU natin is 1.2 times 7.5 plus 1.6 times 15, we have 33 kilonewton per meter. MU natin will be WU L squared all over 8. So 33 times 13 squared all over 8. We have MU over 8 na equal sa 697.125 kilonewton meter. Okay? So, para dun sa required na ZX natin, equals to MU over 3FY. That is 697.125 times 10 to the 6 Newton mm all over 0.9 times 345 Newton per mm squared. Okay? ZX natin required will be 697 times 10 to the 6, 1 to the 6, 0.9 times 345. We have 2,245,169.082 mm cube. So, pwede na lang natin itong gawing 2,245 times 10 cube mm cube. Okay? So, ito yung ZX natin. So, pwedeng gawin nyo is i-select nyo yung, i-convert natin to into inch squared, mm, 1 inch. No? So, 2,245 times 10 to the 3 over 1 over 25.4. Then cube, we have 137 inch cube. No? Ito yung ZX natin. And then punta tayo dun sa ating ZX table. Kailangan natin is 137. So ito, ZX natin 137, 137. So 144 to. So try natin si W21 by 62. Okay? W21 by 62 yung gagamitin natin. So try W21 by 62 natin. Okay? So pag na-select natin yung section, ang gawin natin is kunin natin yung properties niya ay dun sa table natin. Punta tayo dun sa table. So, database natin and then select lang natin dito W21 by 62. 21 by 62. Yan. So, ito si 21 by 62. Kailangan natin para makalculate natin is yung weight niya. Okay, so yung weight ay equal sa 92.0 kilogram per meter. Yung kanyang ano pa yung kailangan natin sa kanya? Yung ZX niya is ito, 2360 times 10 cube, cube. Then, kunin na din natin yung gagamitin natin for shear. Yung D natin, yung K1, tsaka yung TW natin at IX. Okay. So, D natin, IX natin is 554 times 10 to the 6, to the 4th. Depth natin, 533. K1 natin is 20.6. And TW natin is 10.2. Okay? So, check natin for yung section natin for flexure. Kailangan yung Z actual natin is less than dun sa section natin. Okay? So, para magawa yon, so yung WU natin will be equal sa 1.2 times yung 7.5 na superimposed dead load plus yung 92 kilograms times 10.81 all over 1,000 natin para maging kilonewton per meter plus 1.6 ng 15. Okay? So yung WU natin is equals to 1.2, 7.5 plus 92, 9.81 over 1,000 plus 1.6 times 15. So yung W natin is 34.083 kilonewton per meter. So yung MU natin will be equals to yung WU times L squared natin na 13 over 8. So that is 720 kilonewton meter. And then yung Z actual natin, ZX actual is equals to MU over phi Fy. So that will be 720 times 10 to the 6 all over 0.9 times 345. Magiging value natin is 2319 times 10 to the 3 cube, which is less than dun sa ZX actual natin. So therefore, okay. Okay? So itong na-calculate natin is less than dito. So ibig sabihin, kaya nung section natin yung load natin na 720. So sabihin, si 21 by 62 is adequate for texture. Okay? So next is kailangan calculate natin yung kanyang shear capacity. So shear capacity natin is Vn is equals to 0.6 Fy AW tsaka CV. So H over TW is equals to D minus 2 K1 all over TW. So based from the previous slide, ito yung properties natin. Let me copy lang to. Okay, so ito yun. So this will be 533 minus 2 times 20.6 all over 10.2. So HTW natin 533 minus 2 times 20.6 all over 10.2. That is 48.216, which is less than do sa 2.24 na square root of E over Fy. Verify nyo na lang, pero 50 plus di ba yung value nito? So, sabihin CV natin equals to 1.0. So, ang phi natin is equals to 1.0. Okay? So, ang phi Vn is equals to 1.0 times 0.6. Then Fy is 345. AW is D times TW times yung CV na 1.0. So 1.0 times 0.6 times 345 times 533 times 10.2 times 1. Okay? So dividing by 1,000. So ang capacity ng section natin for shear is 1,125.38 kilonewton. Pero ano yung ultimate shear natin? That is WL over 2. So mula dito kanina, so 33 yon. So gawin natin 1.2. Tapos kung ano yung value dito ng W natin. Ito pala dapat, no? So 34.083. So 34.083 times 13.0 squared, WL lang, over 2. So VU natin is over 2. So we have 221.54 kilonewton. Since VU natin is less than sa VVN natin, therefore, okay for section is adequate for shear. Okay? So, okay din siya for shear. Next check is for deflection. Okay? So, yung allowable natin equals to L over 360. So, that is 13,000 mm over 360. So, equals sa 36.11 mm. So, yung value natin is 5 over 384 times WL lang, tapos L to the fourth over EIX. Okay? Kailangan natin value ng IX. So, ito yun. Okay, so this is 5 over 384. Then, yung WL natin is 15 Newton per mm times 13 times 10 to the 3 to the fourth all over E na 200 times 10 to the 3 times IX natin na 554 times 10 to the 6. Okay? So delta is 15, 13 times 10 to the 3 raised to 4, 200 times 10 to the 3, 554 times 10 to the 6. Okay? So makukuha natin times 5 over 384. So makuha natin is 50.346 mm. So greater than siya sa allowable, meaning therefore section is inadequate. Ibig din sabihin deflection controls, no? Ibig sabihin mas critical si deflection. Okay? Kaya kailangan i-base natin yung selection ngayon ng section natin kay deflection. And ang formula natin, di ba, is 5 over 384 WL to the fourth over EIX. So para makuha natin yung required na section natin, kunin natin yung required IX. Or IX natin is equals to 5 over 384 WL to the fourth all over delta. And yung delta natin na yan is kung ano yung limitation natin, which is ito. Pinakalculate natin 36.1. So 5 over 384 times dito is 15 13 times 10 to the 3 to the fourth all over delta natin is 36.11. Okay? So, IX natin required is 5 over 384 15 times 13 times 10 times 3 to the fourth all over 36.11. We have 1, 1544. Wait lang. So 5 over 384 times 15 times 13 times 10 to the 3 to the fourth was divided by 13 times 10 to the 3 over 360. Okay. 1.54545 times 10 to the 14 mm to the fourth. Okay? So, yan yung nakuhang value. So, yan yung titingnan natin dun sa additional table natin. So, punta tayo kay AASC. Yung kanina, selection ng shape by ZX. Pag tingnan natin yung table 3-3, selection by IX siya. No? So, kailangan yung mm to the fourth natin na na-calculate dun sa table natin, i-change natin into inch to the fourth. No? So, convert lang natin. So, ito will be 25.4 mm, then 1 inch. So, divide natin yung 25.4 raised to 4. Okay? So, ang required natin is 371,131,425.9 inch to the fourth. So, yan yung kailangan nating value. And yung percentage sa na IX sa atin, so verify natin yung equation natin. No? Baka may mali. 15, 36.11 mm. Ayun, may nawawala pala doon sa equation natin kaya ang laki ng value. No? So let's go back doon sana natin. Okay? So dito, may nawawala yung E natin dito. No? So before tayo mag-convert, at may E. So 5 over 384 times 15 times 13 times 10 cube, 10 to the 3 to the fourth over 200 times 10 to 3 and then 36.11. Okay, yeah. So we have 5 times 15 times 13 times 10 to the 3 to the fourth all over 384, 200 times 10 to the 3, 36.11. Okay, so we have 772,406,578.9 mm to the fourth. Convert natin into inches to the fourth. Equals din yan sa 1856, no? Rounded off to inch to the fourth. So, may 1856 na tayo. Yan yung kailangan natin dito sa ice shape natin. So, kunin natin yung 1856 greater than 1856. So, tinig dito. Next. 3610, 1856 lang tayo. 1830. This is 21. So, W24 by 76. Okay? So, yun yung kasunod na pwede, no? Double ito. 1830 lang to. Kailangan natin is 1856. Kaya W24. Try natin si W24 by 76. Okay? Meron siyang IX na 2,100 inch to the fourth. Okay? So, try W24 by 76. Okay? So, ibig sabihin, ito, kung ito yung pipili natin, pasado na sa deflection niya automatically, no? Kahit hindi na natin i-recheck. Ang kailangan natin i-verify ngayon is what is its value kapag check natin yung flexural capacity niya o ibig sabihin yung ZX niya tsaka yung sa shear capacity. Okay? So, kunin lang natin yung length, yung lahat ng parameters na kailangan natin. So, babaguhin natin to. Gagawin natin 24 by 76, no? So, 24 by 76. Okay, so ito yung 24 by 76. Kailangan natin is yung weight niya para sa checking natin ng weight, ang dead load, um, W. Okay, ito, 113 kilogram per meter. Kailangan din natin yung ZX niya, yung IX, yung value ng D, nung kanyang K1, tsaka TW. Okay, so isa-isa na lang natin. Dito, TW is 11.2. Ang depth natin is 607. Ang K1 natin is 36.5. ZX and IX natin, ito, IX natin is 874 times 10 to the 6 mm to the 4th. Then ang ZX is 3280 times 10 to the 3 mm to the 3. Okay? So, going back to sa slide natin. Okay? Ayan. Check natin ulit for Flexure. So, kailangan natin is yung WU natin is equals to 1.2 plus yung 7.5 times 7.5 plus yung weight natin na 113 times 9.81 over 1,000 para maging kilonewton per meter plus 1.6 nung ating um, live load. Okay? So yung WU natin is 1.2, 7.5 plus 113 times 9.81 over 1,000 plus 1.6 times 15. Okay? So ito ay 34.33 kilonewton meter. So yung MU natin, substitute na lang. Answer times 13 squared over 8, that is equals to 725.226 kilonewton meter. So yung Z X actual natin is equals to MU over PFY. So 725.226 times 10 to the 6 all over 0.9 times 345. So equals tayo sa moment over 0.9 plus 345, that is equals to 2336 times 10 cube mm cube. Okay? Which is, kung i-check natin, this value is less than dito sa ZX natin ng section. Okay? Therefore, okay sa flexure, no? Okay? Next is yung sa ating shear. So shear natin is equals to 0.6 Fy AW CV. So H over TW natin is equals to D minus 2K1 all over TW, that is 607 minus 2 times 36.5 all over TW is 11.2. So 607 minus 2 times 36.5 all over 11.2, that is equivalent to 47, no? 0.68, which is less than dun sa 2.24 squared of E over Fy. Therefore, CV natin is equals to 1.0. So, ang phi natin is also 1.0. So, ang PVN will be equals to 1.0 times 0.6 times yung Fy natin at 345, AW na D times TW, and then 1.0 na CEV. So yung PVN natin is equals to 0.6, 345, 607, 11.2 times 1. So yung ating capacity is 1407.27 kilonewton. And then yung VU natin is equals to WU L over 2. That is 34.33 times 13 over 2 is equals to 13 over 2. So 223.145 kilonewton. Na since VU is less than sa VN natin, therefore, okay for shear. So, sabihin, use W 24/76 as our most economical section for this problem. Okay? So, ayan. So, medyo nagbago yung atake dito kasi yung mismong deflection natin is nag-fail dun sa allowable natin. Kaya ibig sabihin, mas critical sa deflection. Kaya binase natin kay deflection yung pagkuha ng value ng section natin, which is pwede natin gawin kapag IX natin. Okay? So yung formula na to again is for uniformly distributed on simply supported lang. Pag nag-iba yung condition ng loading, iba na po yung value niyan. So you have to be very careful with that. So you also have to refer ulit doon sa structural theory ninyo to identify yung deflection ng ibang loading condition. Okay? Pero dito, i-recap lang natin for this problem, yung una natin ginawa is chinek natin for flexure. May nakuha tayong unang section na 21/62. Pero upon checking, this particular section fails dun sa ating deflection. Kaya nag-try ulit tayo by another section, 24/76, na pagka-check natin, pasado na siya sa flexure, pasado siya sa shear. And of course, since this is based from the requirement of the deflection, pasado na din siya sa deflection. So, therefore, use natin tong section na to. Okay? So, yan. So, ganyan po yung pag-select o pag-design ng beam natin when subjected to SDL natin o superimposed loadings natin. Okay? Question? Okay, so if you find any concern dito sa way ng pag-solve natin, please don't hesitate to reach out dun sa ano natin, no, sa GC natin. I have here, okay lang ba unang computing yung deflection? Okay lang din naman unang computing yung deflection, pero ang problem mo kasi wala kang section. Hindi mo alam yung section na gagamitin mo. So hindi mo alam yung value ng IX and SX mo or ZX mo. Pwedeng mauna yung deflection, pero hindi kasi lagi nagko-control sa deflection no? So kung pwede naman mauna sa deflection para magkameron ka ng initial na section, tapos kapag hindi pumasa sa checking ng flexure tsaka ng shear, and then adjust ka doon sa kasunod sa na section dun sa table natin sa AISC. Pero yes, pwedeng maunang computing yung deflection. If you want to design or to select your section based from deflection requirements, okay lang din. Okay? Okay, so ayan. So other question anymore? Anyone? Okay, so kung wala na question, this ends our lecture for today. And ayan, yun yung kung paano mag-design ng ating flexural beam. So, ang magiging last topic natin for this subject will be design ng member sa combination ng axial tsaka ng flexure na tayo. Combined axial and flexure. So, ibig sabihin yung design ng compression tsaka design ng flexure, combined naman siya sa analysis. Okay? So, yun yung di-discuss natin sa prior weeks. Pero for now, this ends our lecture for today. Thank you.